Rebar, from Wikipedia, the free encyclopedia. For other uses, see rebar, disambiguation. This article needs additional citations for verification. Please help improve this article by adding citations to reliable sources. Unsourced material may be challenged and removed. January 2008. Learn how and when to remove this template message. Rebar, short for reinforcing bar, is collectively known as reinforcing steel and reinforcement steel. It is a steel bar or mesh of steel wires used as a tension device in reinforced concrete and reinforced masonry structures to strengthen and hold the concrete in compression. Concrete is strong under compression but has weak tensile strength. Rebar significantly increases the tensile strength of the structure. Rebar's surface is often patterned to form a better bond with concrete. The most common type of rebar is carbon steel, typically consisting of hot-rolled round bars with deformation patterns. Other readily available types include stainless steel and composite sections made of glass fiber, carbon fiber, or basalt fiber. These alternate types tend to be more expensive or have less mechanical properties and are thus more often used in specialty construction where their physical characteristics fulfill a specific performance requirement that carbon steel does not provide. In practice, any material with sufficient tensile strength that is materially compatible with concrete could potentially be used to reinforce concrete. For example, bamboo might be considered a viable substitution in regions where steel is not available. Steel and concrete have similar coefficients of thermal expansion, so a concrete structural member reinforced with steel experience minimal strength as the temperature changes. History. Reinforcing bars in masonry construction have been used since at least the 15th century. 2,500 meters of rebar was used in the Chateau de Vincennes during the 18th century. Rebar was used to form the carcass of the Leaning Tower of Neviansk in Russia, built on the orders of the industrialist Akinfi Demidov. The cast iron, citation needed, used for the rebar was of high quality, and there is no corrosion on the bars to this day. The carcass of the tower was connected to its cast iron tented roof, crowned with one of the first known lightning rods. However, it was not until the mid-19th century that rebar displayed its greatest strengths with the embedding of steel bars into concrete, thus producing the modern reinforced concrete. Several people in Europe and North America developed reinforced concretes in the 1850s. These include Joseph Louis Lambot of France, who built reinforced concrete boats in Paris, 1854, and Thaddeus Hyatt of the United States, who produced and tested reinforced concrete beams. Joseph Monnier of France is one of the most notable figures for the invention and popularization of reinforced concrete. As a French gardener, Monnier patented reinforced concrete flower pots in 1867 before proceeding to build reinforced concrete water tanks and bridges. Ernest L. Ramsum, an English engineer and architect who worked in the United States, made a significant contribution to the development of reinforcing bars and concrete construction. He invented twisted iron rebars, which he initially thought of while designing self-supporting sidewalks for the Masonic Hall at Stockton, California. His twisted rebar was, however, not initially appreciated and even ridiculed at the Technical Society of California, where members stated that the twisting would weaken the iron. In 1889, the Ramsum worked on the West Coast, mainly designing bridges. One of these, the Alvord Lake Bridge in San Francisco's Golden Gate Park, was the first reinforced concrete bridge built in the United States. He used twisted rebar in this structure. At the same time, Ernest L. Ramsum was inventing twisted steel rebar. C.A.P. Turner was designing his mushroom system of reinforced concrete floor slabs with smooth round rods, and Julius Kahn, inventor, was experimenting with an innovative rolled diamond-shaped rebar with flat-plate flanges angled upwards at 45 degrees, patented in 1902. Kahn predicted concrete beams with the reinforcing system would act in bending like a Warren truss, and also thought of these rebars as shear reinforcement. Kahn's reinforcing system was built in concrete beams, joists, and columns. This system was both praised and criticized by Kahn's engineering contemporaries. C.A.P. Turner voiced strong objections to this system as it could cause catastrophic failures to concrete structures. He rejected the idea that Kahn's reinforcing system in concrete beams would act as the Warren truss, and also noted that this system would not provide the adequate amount of shear stress reinforcement at the ends of the simply supported beams, the place where the shear stress is greatest. Running out of water. Furthermore, Turner warned that Kahn's system could result in a brittle failure as it did not have longitudinal reinforcements in the beams at the columns. This type of failure unfortunately manifested itself in the partial collapse of the Bixby Hotel in Long Beach, California, and total collapse of the Eastman Kodak building in Rochester, New York, both during the construction in 1906. It was, however, conducted that both failures were consequences of poor quality labor, with increase in demand of construction standardization. Innovative reinforcing systems such as Kahn's were pushed to the side in favor of the concrete reinforcing systems seen today. Requirements for deformations on steel bar reinforcement were not standardized in U.S. construction until about 1950. Modern requirements for deformations were established in tentative specifications of the deformations of deformed steel bars for concrete reinforcement, ASTM A305-47T. Subsequently, changes were made that increased rib height and reduced rib spacing for certain bar sizes, and the qualification of tentative was removed when the updated standard ASTM A305-49 was issued in 1949. The requirements for deformations found in current specifications for steel bar reinforcing, such as ASTM A615 and ASTM A706, among others, are the same as those specified in ASTM A305-49. Use in concrete masonry. Oh man, I'm running out of water. Primary reinforcement and secondary reinforcement. Read right here for primary. For primary reinforcement and secondary reinforcement in psychology, operant conditioning, see reinforcement, primary reinforcers, and reinforcement and secondary reinforcers. Concrete is a material that is very strong in compression but relatively weak in tension. To compensate for this imbalance in concrete's behavior, rebar is cast into it to carry tensile loads. Most steel reinforcement is divided into primary and secondary reinforcements, and there are other minor uses. Primary reinforcement refers to the steel which is employed to guarantee the resistance needed by the structure as a whole to support the design loads. Secondary reinforcement, also known as distribution or thermal reinforcement, is employed for durability and aesthetic reasons, by providing enough localized resistance to limit cracking and resist stresses caused by effects such as temperature changes and shrinkage. Rebar is also employed to confer resistance to concentrated loads by providing enough localized resistance and stiffness for a load to spread through a wider area. Rebar may also need to be used to hold other steel bars in the correct position to accommodate their loads. Those are called stirrups. External steel tie bars can constrain and reinforce masonry structures, as illustrated in the Neviansk Tower or ancient structures in Rome and the Vatican. Masonry structures and the mortar holding them together have similar properties to concrete and also have limited ability to carry tensile loads. Some standard masonry units, like block and bricks, are made with voids to accommodate rebar, which is then secured in place with grout. The combination is known as reinforced masonry. Physical characteristics. Steel has a thermal expansion coefficient nearly equal to that of modern concrete. If this were not so, it would cause problems through additional longitudinal and perpendicular stresses as temperatures different from the temperature of a setting. Although rebar has ribs that bind it mechanically to the concrete, it can still be pulled out of the concrete under high stresses, an occurrence that often accompanies a larger scale collapse on the structure. To prevent such failure, rebar is either deeply embedded into adjacent structural members, 40 to 60 times the diameter, or bent and hooked at the ends to lock it around the concrete and other rebar. The first approach increases the friction locking of the bar into place, while the second makes use of the highly compressive strength of concrete. Common rebar is made of unfinished tempered steel, making it susceptible to rusting. Normally, the concrete cover is able to provide a pH value higher than 12, avoiding the corrosion reaction. Too little concrete cover can compromise this guard through carbonation from the surface and salt penetration. Too much concrete cover can cause bigger crack widths, which also comprises the local guard, as rust takes up greater volume than the steel from which it is formed. It causes several internal pressure on the surrounding concrete, leading to cracking, spalling, and ultimately structural failure. This phenomenon is known as oxide jacking. This is a particular problem where the concrete is exposed to salt water, as in bridges where salt is applied onto roadways in winter, or in marine applications. Uncoated, corrosion-resistant, low-carbon chromium microcomposite, epoxy-coated, galvanized, or stainless steel rebars may be employed in these situations at greater initial expense, but significantly lower expense over the service life of the project. Extra care is taken during the transport, fabrication, handling, installation, and concrete placement process when working with epoxy-coated rebar, because damage will reduce the long-term corrosion resistance of these bars. Even damaged bars have shown better performance than uncoated reinforcing bars, though issues from the bonding of the epoxy coating from the bars and corrosion under the epoxy film have been reported. These bars are used in over 70,000 bridges in the United States. The requirements for deformations are found in standard product specifications for steel bar reinforcing, such as ASTM A615 and ASTM A706, and dictate lug, spacing, and height. Fiber-reinforced plastic rebar is also used in high corrosion environments. It is available in many forms, such as spiral or reinforcing columns, common rods, and meshes. Most commercially available rebar is made from unidirectional fibers set in thermoset polymer resin and is often referred to as FRP. Hold on, let me get some water. They're running out. Some special constructions, such as research and manufacturing facilities with very sensitive electronics, may require the use of reinforcement that is not conductive to electricity. Any medical imaging equipment rooms may cover non-magnetic properties to avoid interference. FRP rebar, notably glass fiber types, have low electrical conductivity and are non-magnetic, which is commonly used for such needs. Stainless steel rebar with low magnetic permeability is also and is sometimes used to avoid magnetic interference issues. Reinforcing steel can also be displaced by impacts such as earthquakes, resulting in structural failure. A prime example of this is the collapse of the Cypress Street Viaduct in Oakland, California, as a result of the 1989 Loma Prieta earthquake, causing 42 fatalities. The shaking of the earthquake caused rebar to burst from the concrete and buckle. Updated building designs include more circumferential rebar can address this type of failure. Sizes and grades. U.S. imperial sizes give the diameter in units of 1/8 of an inch for bar sizes number 2 through number 8, so that number 8 over 8 inch, is equal to 1 inch in diameter. The cross-sectional area given by pi r squared works out to bar size per 9.027 to the power of 2, squared, which is approximately as bar size over 9 square inches. For example, the area of number 8 rebar is 8 over 9 squared, which is 0.79 square inches. Bar sizes larger than number 8 follow the 1/8 inch rule imperfectly and skip sizes 12 to 13 and number 15 to 17 due to historical convention. In early construction, bars 1 inch and larger were only available in square sections, and when large deformed round bars became available around 1957, the industry manufactured them to provide the cross-sectional area equivalent of standard square bar sizes that were formerly used. The diameter of each equivalent format round shape is rounded to the nearest 1/8 of an inch to provide the bar size. For example, number 9 has a cross-section of 1 square inches and therefore a diameter of 1.128 square inches. Number 10, 11, 14, and 18 sizes correspond to 1/1/8 of an inch, 1 1/4, 1 1/2, and 2 inch square bars respectively. Number 14 rebar is particularly affected by this approximation. By diameter, it would be number 13.5. Sizes smaller than number 3 are no longer recognized as standard sizes. These are commonly manufactured as plain, round, undeformed rod steel, and can be made with deformations. Sizes smaller than number 3 are typically referred to as wire products and not bar, and specifically by either their nominal diameter or wire gauge number. Number 2 bars are often informally called pencil rod, or they are about the same size as a pencil. When U.S. imperial size rebar are used in projects with metric units, the equivalent metric size is typically specified as the nominal diameter rounded to the nearest millimeter. These are not considered standard metric sizes, and thus is often referred to as a soft conversion or the soft metric size. The U.S. imperial bar size system recognizes the use of true metric bar sizes, numbers 10, 12, 16, 20, 25, 28, 32, 36, 40, 50, and 60 specifically, which indicates the nominal bar diameter in millimeters as an alternate size specification. Substituting a true metric size for a U.S. imperial size is called a hard conversion, and sometimes results in the use of a physically different sized bar. There are no fractional bar sizes in this system. The number symbol in this system indicates the number sign, and thus number 6 is read as number 6, and the use of the number sign is customary for U.S. sizes. However, NO period is sometimes used instead. I'm not reading that chart. Canadian sizes. Metric bar designations represent the nominal diameter in millimeters rounded to the nearest 5 millimeters. European sizes. Metric bar designations represent the nominal bar diameter in millimeters. Preferably, bar sizes in Europe are specified to comply with Table 6 of the standard EN 100080. Although various national standards still remain in force, example BS 4449 in the United Kingdom, in Switzerland some sizes are different from European standard. Australian sizes. Reinforcement for use in concrete construction is subject to the requirements of Australian standards AS 3600-2009 concrete structures and AS/NZS 4671-2001 steel reinforcement for concrete. There are other standards that apply to testing, welding, and galvanizing. The designation of reinforcement is defined as AS/NZS 4671-2001 using the following formats. I'm not reading that. Bars are typically abbreviated to simply N, hot rolled deformed bar, R, hot rolled round bar, RW, cold drawn ribbed wire, or W, cold drawn round wire. As the yield strength and ductility class can be implied from the shape. For example, all commercially available wire has a yield strength of 500 megapascals and low ductility, while round bars are 250 megapascals and normal ductility. India. Rebars are often available in the following grades as per IS 1786-2008 FE415/FE415D/FE500/FE550D, FE600. Rebars are quenched with water at a high level pressure so that the outer surface is hardened while the inner core remains soft. Rebars are ribbed so that the concrete can have a better grip. Coastal regions use galvanized rebar to prolong their life. Weight charts of Indian rebars with tolerances and sizes. Jumbo and threaded bar sizes. Very large format rebar sizes are widely available and produced by specialty manufacturers. The tower and sign industries commonly use jumbo bars as anchor rods for large structures, which are fabricated from slightly oversized blanks such that threads can be cut at the ends to accept standard anchor nuts. The fully threaded rebar is also produced with very coarse threads which satisfy rebar deformation standards and allow to custom nuts and couplers to be used. Note that these customary sizes, while in common use, do not have consensus standards associated with them, and actual properties may vary by manufacturer. Grades. Rebar is available in grades and specifications that vary in yield strength, ultimate tensile strength, chemical composition, and percentage of elongation. The use of grade by itself only indicates the minimum permissible yield strength, and it must be used in the context of a material specification in order to fully describe the product requirements for rebar. Material specifications set the requirements for grade as well as additional properties such as chemical composition, minimum elongation, physical tolerances, etc. Fabricated rebar must exceed the grade's minimum yield strength, and any other material specification requires when inspected and tested. In U.S. use, the grade designation is equal to the minimum yield strength of the bar in KSI, 1,000 pounds per square inch. For example, grade 60 rebar has a minimum yield strength of 60 KSI. Rebar is most commonly manufactured in grades 40, 60, and 75 with higher tensile strength, with higher strength readily available in grades 80, 100, 120, and 150. Grade 60, 420 megapascals, is most widely used rebar in modern U.S. construction. Historic grades include 30, 33, 35, 36, 50, and 55, which are not in common use today. Some grades are only manufactured for specific bar sizes. For example, under ASTM A615, grade 40, 280 megapascals is only furnished for U.S. bar sizes numbers 3 through 6. Soft metric number 10 through 19. Sometimes limitations on available material grades or specific rebar specific bar sizes is related to the manufacturing process used, as well as the availability of controlled quality raw materials used. I think now is a good time for a checkpoint. So at this stage of the checkpoint, please type out something that you learned from our little talk on rebar. Type it in the comment section below, and just to show that you care. Resuming. Some material specifications cover multiple grades, and in such cases it is necessary to indicate both the material specification and grade. For example, material specification ASTM A615 has 4 grades, 40, 60, 75, and 80, and one would need to indicate ASTM A615 grade 60 to be unequivocal. On the other hand, material specification ASTM A706 only has 1 grade, which is 60. Therefore, indicating ASTM A706 is technically equivalent to ASTM A706 grade 60. However, the latter is ambiguous. Rebar grades are customarily noted on engineering documents, even when there are no other grade options with the material specification, in order to eliminate the confusion and avoid potential quality issues such as might occur if a material substitution is made, note that GR period is the common engineering abbreviation for grade, while variations on letter capitalization and use of the period. In certain cases, such as earthquake engineering and blast-resistant design where post-yield behavior is expected, it is important to be able to predict and control properties such as the maximum yield strength and minimum ratio of tensile strength to yield strength. ASTM A706 is an example of controlled property range material specification which has a minimum yield strength of 60 ksi or 420 megapascals, maximum yield strength of 78 ksi, 540 megapascals, minimum tensile strength of 80 ksi, 550 megapascals, and not less than 1.25 times the actual yield strength, and minimum elongation requirements that vary by bar size. In countries that use the metric system, the grade designation is typically the yield strength in megapascals. MPa, for example, grade 400, similar to US grade 60, however, metric grade 420 is actually the exact substitution for the US grade. Common US specifications published by ASCI and ASTM are all of that. I'm not reading that. Historically in Europe, rebar is composed of mild steel material with a yield strength of approximately 250 megapascals or 36 ksi. Modern rebar is composed of high-yield steel, with a yield strength more typically 500 megapascals, 72.5 ksi. Rebar can be supplied with various grades of ductility. The more ductile steel is capable of... Whoops, sorry, I dropped the microphone there. Oh, that wasn't too loud. Sorry, where was I? The more ductile steel is capable of absorbing considerably more energy when deformed. A behavior that resists earthquakes, forces, and is used in design. These high-yield strength ductile steels are usually produced using the temp core process, a method of thermochemical processing. The manufacture of reinforcing steel by re-rolling finished products, example sheets or rails, is not allowed. In contrast to structural steel, rebar steel grades are not harmonized yet across Europe, each country having their own national standards. However, some standardization of specification and testing methods exist under EN 10080 and 10080 and EN ISO 15630. I'm not reading that. Placing rebar. Rebar cages. Oh, I'm lagging. Okay. Placing rebar. Rebar cages either on or off the project site, commonly with the help of hydraulic benders and shears. However, for small or custom work, a tool known as a hickey or hand rebar bender is sufficient. The rebar are replaced by steel fixers, rod busters, or concrete reinforcing iron workers with bar supports and concrete over plastic. Rebar spacers used in separating the rebar from the concrete framework to establish concrete cover and ensure that proper embedment is achieved. The rebar in the cages are connected by spot welding, tying steel wire, sometimes using an electric rebar tier, or with mechanical connections. For tying epoxy-coated or galvanized rebars, epoxy-coated or galvanized wire is normally used respectively. Stirrups. Stirrups form the outer part of the rebar cage. Stirrups are usually rectangular and are placed at regular intervals along a column or beam to prevent shear failure. Welding. The American Welding Society, AWS, D1.4 sets out the practices for welding rebar in the U.S. Without special consideration, the only rebar that is ready to weld is W grade, low alloy A706. Rebar that is not produced to the ASTM A706 specification is generally not suitable for welding without calculating the carbon equivalent material. Material with a carbon equivalent of less than 0.55 can be welded. ASTM A616 and ASTM A617, now replaced with a combined standard of A996, reinforcing bars are re-rolled rail steel and re-rolled rail axle steel with uncontrolled chemistry, phosphorus and carbon content. These materials are not common. Rebar cages are normally tied together with wire, although spot welding of cages has been norm in Europe for many years and is becoming more common in the United States. High-strength steels, for pre-stressed concrete may absolutely not be welded. Mechanical connections. Also known as mechanical couplers or mechanical spikes, mechanical connections are used to connect reinforcing bars together. Mechanical couplers are an effective means to reduce rebar congestion in highly reinforced areas for cast-in-place concrete construction. These couplers are also used in precast construction at the joints between members. The structural performance criteria for mechanical connections varies between countries, codes, and industries. As a minimum requirement, codes typically specify that the rebar to splice connection meets or exceeds 125% of the specified yield strength of the rebar. More stringent criteria also requires the development of the specified ultimate strength of the rebar. As an example, ACI 318 specifies either Type 1 120% FY or Type 2 125% FY and 100% FU performance criteria. Hold on, let me get a drink. My throat's really dry. Oh, that's good water. Okay, resuming. For concrete structures designed with ductility in mind, it is recommended that the mechanical connections are also capable of failing in a ductile manner, typically known in the reinforcing steel industry as achieving bar break. As an example, Caltrans specifies a required mode of failure, example, necking of the bar. Safety. To prevent injury, the protruding ends of steel rebar are often bent or covered with a special steel plastic plate caps. Mushroom caps may provide protection from scratches and other minor injuries, but provide little to no protection from impalement. Designations. Reinforcement is usually tabulated in a reinforcement schedule on construction drawings. This eliminates ambiguity in the notations used around the world. The following list provide examples of the notations used in the architectural, engineering, and construction industry. Designation. HD-16-300 TNB EW, high strength 500 megapascals, 16 mm diameter rebars spaced at 300 mm center to center distance on both the top and bottom face and in each way as well, longitudinal and transverse. 3D12, 3 mild strength, 300 megapascals, 12 mm diameter rebars. R8 stirrups at 225 max. D grade, 300 megapascals, smooth bar stirrups, spaced at 225 mm centers. By default in New Zealand, practice all stirrups are normally interpreted as being full, closed loops. This is a detailing requirement for concrete ductility in seismic zones. If a single strand of stirrup with a hook at each end was required, this would typically be both specified and illustrated. United States. Number 4 at 12 off center, TNB EW. Number 4 rebar spaced 12 inches on center to center distance, on both the top and bottom faces in each way as well. Example, longitudinal and transverse. 3. Number 4. 3 number 4 rebars. Usually used when the rebar perpendicular to the detail. Number 3 ties at 9 off center. Number 2, 2%. Number 3 rebars use a stirrup spaced at 9 inches on center. Each consists of 2 ties, which is usually illustrated. Number 7 at 12 inches, EW at EF. Number 7 rebar spaced 12 inches apart, placed in each direction, each way and on each face. Reuse and recycling. In China and many other countries, after the demolition of a concrete structure, workers are called to remove the rebar. They scour the site, extracting the metal using bolt cutters, welding equipment, sledgehammers, and other tools. The metal is partially straightened, bundled, and sold. Rebar, like almost all metal products, can be recycled as scrap. It is usually combined with other steel products, melted down, and reformed. Oh shit. That read was a lot longer than I thought it would be. Okay, so that concludes this video. Thank you for watching, and I'll see you guys later. Take care. Bye.